Okay, let's get started. It's a minute after. So welcome everyone to day 6 of Organometallics. A couple quick administrative reminders. Many people have already sent in their Wikipedia articles or at least started discussing how they want to refine their idea. So if you haven't done so, please do so ASAP. It's due today. And then another reminder is that the first homework set will be due in about a week and a half now. And your TAs have kindly arranged to hold office hours if you have any questions about those. So there was a poll that was sent out. If you didn't fill that out, or if none of the times that were posted work for you, then just please let me know or let the TAs know. We're always happy to discuss any questions you might have. We'd prefer to do so earlier than later. So as I've said before, please take a look through all the problems to orient yourself if you haven't done so already. So let's jump in. We've got a lot of ground to cover today. We're going to wrap up reductive elimination in the form of the final 2 problems of the day from last time. And then we're going to zoom right ahead through 2 flavors of migratory insertion, 1.1 and 1.2. Then we'll talk about the microscopic reverses of those 2 processes, alpha elimination and beta elimination. And then we'll conclude with a discussion of transmetallation. And hopefully, as I said before, this will give you, this is not an exhaustive list of all elementary steps ever observed with organometallic complexes, but hopefully it will give you a good foundation and will serve in essence as the alphabet for you to be able to compose these catalytic cycles, which will be the main focus of the second half of the class. Okay, let's jump in by rewinding to problem of the day number 5. If you remember, we so a problem of the day from day 5, problem 2. If you remember, we left off with the poll in comparing the 2 reductive elimination rates of complex A and B shown here. And then I encourage you to think about B and C over the past 2 days. Hopefully you had a chance to do so. And then now we'll I'll call on some volunteers to offer an answer and then propose their experiment. So let me see, can I see everybody that's on? I can never tell if I can see the whole list of names. Is Mario on? I don't think I see his name. How about Aaron? Okay, getting to the bottom of the cup until resetting. What about Sunghan?
So I think the methyl aldehyde may be addition to the palladium.
Okay. What kind of addition?
Oxidative addition.
Okay. And then what would that yield?
I think it will form a octahedral complex.
Okay. And palladium in what oxidation state?
+4.
Okay. And then what would happen?
So I'm not sure, but I think there are 2. The complex will become more crowded, so the SN is tend to be released. That's what I think.
Okay. Let me draw that out. Is everyone able to see my iPad? Yeah, okay, thanks. So Sunghan proposed that we have this trans-spanning ligand that we talked about. And Sunghan proposed oxidative addition to a palladium 4 intermediate that would look like this. Let me draw this oxidation state more clearly. Sunghan said that it was octahedral, but in practice, it's hard for the 6th ligand to coordinate because of this trans-spanning ligand. So let's let's call this square pyramidal with that 6 coordination site that would be like at the top of this umbrella open. And then you had said that from this intermediate now it's more sterically crowded. Palladium is more electron poor, so reductive elimination can take place more rapidly. Is that correct? So this, and then we would have iodide here resulting from that save addition. Is that a correct summary of your proposed explanation, Sung-Han? Great. And did anybody else get anything different? This is one of these cases where, you know, the more mechanisms, the better, so that part B, the experiments can be more cleverly designed. Any other thoughts here?
I'm wondering if the methyl iodide could matter like one of the phosphine ligand, because the phosphonium and basically you release one of, make it become monodentate, and you can push the methyl group nearer to the cis position.
Okay, that's an interesting idea. So the idea here, if I understand correctly, is you would, I think the issue I see is that the lone pair that you would need for the alkylation is already engaged in bonding to palladium. So you need to first dissociate that. That's gonna, you know, we saw what chelation buys you in terms of equilibrium constant. That's gonna be disfavored by something like 10 to the 5th in the KQ and then get alkylated. So that would be my concern, but I think it is a good thing to think about. So your explanation, maybe before I destroy this structure, let me see if I can redraw this. Would be something like this, methyl. Now this is alkylated, and this allows for the 2 methyl groups to become adopt a cis relationship and then reductively eliminate. Okay, there's 2 good competing hypotheses. Any other thoughts? One that I thought might be reasonable if you had never encountered these types of complexes before is just thinking an analogy to a palladium alkyl like Grignard or an alkyl lithium and directly attacking methyl iodide as an electrophile. I think that would be another potential mechanism. Okay, and then any thoughts for mechanistic experiments that would corroborate a mechanism or ideally exclude some of these competing mechanisms? I can call on someone. Omar?
I have an idea, I think.
Sure.
Would phosphorus NMR help you with the second one, that like if you had dissociation of one of the phosphorus ligands, you would see that in an NMR?
Great. I think that's a good suggestion, Alex. Any other thoughts here?
Oh, I was gonna say you can label the methyl.
Which methyl?
Methyl iodide.
The methyl of methyl iodide. So let's call that this one. And then what would you expect to see, Omar?
That it's in the product.
How many times?
Just once.
One. Okay. And that would be consistent. That would rule out also pathway 2 and be consistent with the palladium 4 pathway. That would, I think you'd still see that product potentially in this Grignard type pathway. And I have to be honest, that Grignard type pathway might be a little bit tricky to rule out. And any thoughts there?
I think maybe we can change the structure of the ligand to add to change the methyl group to some other groups which could not undergo a reductive elimination with methyl iodide. And if we use this kind of ligand, we can see if the phosphorus could combine with methyl.
Okay, so you're still talking about the phosphonium mechanism changing the trans-spanning ligand, and then comparing CP versus CC reductive elimination. Is that right?
Yeah, if the combination could not happen, it means it could not undergo this mechanism.
Okay. Okay, in the interest of time, we'll wrap things up. Thanks everybody for, for this Grignard pathway, some of the things you could think about are like, think about good electrophiles that react with organometallic reagents like a aldehyde or a ketone that would not be expected to be oxidizing enough to promote the 2 to 4 oxidative addition. And then you could run those experiments and see if they react or not. That's just off the top of my head. But sometimes these is really interesting with strong inference. Always, sometimes oftentimes the mechanisms that seem intuitively kind of crazy are ones that are hard to actually disprove. Okay, very good. So just to kind of wrap up the discussion of reductive elimination, which we went through quickly, we talked about different factors that can promote reductive elimination. Again, the opposite trends here to oxidative addition, the difficulties inherent in C heteroatom reductive elimination. And then one thing I did want to spend just a minute touching base on what was the mechanisms by which reductive elimination can take place. And here there's some dependency on the geometry of the parent complex. And here too, there's a clear parallel between the mechanisms of oxidative addition. So with octahedral complexes, you have a prior to reductive elimination, often you'll have ligand dissociation as a first step. Alternatively, when the metal is fully coordinatively saturated, well, it's 6 coordinate, you can have what are called the SN2 type pathways, where the alkyl fragment that's bound to the metal serves as an electrophile. And this is a stereo invertive at the carbogenic group. With square planar complexes, you have more possibilities. You can either have an associative pathway. So think here like coordination of a pi accepting ligand that can reduce electron density at the metal and then trigger reductive elimination from a square pyramidal type intermediate. A dissociative pathway where the complex will get down to 3 coordinate and then reductively eliminate. And then you can also have a non-dissociative pathway where the 4 coordinate metal directly undergoes reductive elimination. But it should be stated here as a caveat that depending on the ligands, as you saw above, sometimes you would need a cis to trans isomerization to take place for that pathway to be in play. Okay, so now let's start to put some of these elementary steps together and have a teaser for what we're going to cover more of in the different catalytic cycles that we'll go through in class. So to do this, we'll take a look at from day 5, problem of the day number 3. So first, part A, can someone help? And that's the pre-catalyst for this is this interesting looking palladium dimer species. Eleanor, could you help us with electron counting and for this?
Yeah, sure. So you have the 2 phosphine L types, and then I think the iodines count as LX if they're bridging. So then I think that the palladium oxidation state is palladium 2.
Okay, let's quickly go through this. So you said you have, let's just consider, let's say just the left palladium, because this is a symmetric complex, so both of them will be the same. You've got 1 phosphine ligand, which is L type, and then the iodides, one, as you said, one will serve as X type and one will serve as L type. So let's just draw that out. And then you have this palladium-palladium bond, which won't affect the oxidation state assignment. So you've got 1L, 2L.
Yeah, palladium 1.
Okay, right?
Okay, so then
And that's
D9.
D9. Okay.
So then I think overall it's 16 electrons for the palladium, or did I make?
Okay, so you've got 9 electrons coming from the D9 metal, and then you've got 3 times 2 from the ligands. That brings you to 15, and then 1 from the metal-metal bond equals 16. Is that what everybody got? And oh, we'd also asked for coordination number. What do you think for coordination number here?
4.
4, okay. Yeah, I guess the only point of uncertainty would be the metal-metal bond, whether you count that, and generally we're defining it as electron pairs participating in bonding, so we can count that. Again, if there's something sneaky like that on a test, then you can always just explain your reasoning, and that's fine. Okay, and what about B? So there's this observation that the monomeric versions of this catalyst don't affect this transformation. So Stone, what do you think for mechanism here?
I think
So overall, you know, you can look at the product and know that you need to form this carbon sulfur bond. So what are the things that are going through your mind about what steps need to happen? And then we can talk about what order is most reasonable. Are you there, Stone?
yeah.
Oh, okay.
We need an oxidative addition.
Okay. I agree with that. And then we're also going to need to carbon sulfur bond formation. So let's say we also need a reductive elimination at some point. And then we need to get both of these onto the metal. So let me give a quick hint that I don't think you would be able to maybe predict a priori, or if you did, then you know more about thio. What are these called? Phosphothiolates than I do, which is that the first step is actually ligand exchange, or I think the authors call it transmetallation, but let's call it ligand exchange. And this can be established just by doing a stoichiometric experiment and looking at the NMR. And so then you said the next step is oxidative addition. How do you envision that happening? And then in a way that's consistent with the observation that just simple monomeric catalysts don't undergo this reaction.
I guess maybe the metal-metal bond is nucleophilic.
Okay, I like the general thinking that the metal-metal bond is somehow involved. One of the things we covered last class was this possibility of bimetallic oxidative addition, where the two metals can share. So they're both, as Eleanor told us, they're both +1 in the starting material. Palladium in the +1 oxidation state is still quite electron rich, so it's capable of adding to aryl iodides. And in this case, the two metals undergo aryl iodide oxidative addition across them, and they share the overall +2 oxidation state across the metals so that each of them becomes palladium 2. And then now the last step is you have this syn configured, and I won't draw this just in interest of time, these cis configured sulfur, which is nucleophilic, and the aryl group, which can undergo reductive elimination. And then the iodide can swing back around to regenerate the pre-catalyst.
Hey, Kiri, with that oxidative addition right there, in the event that the aryl group is where the iodide is, like, would that just undergo a reductive elimination of the same material until it funnels to the synphase?
Well, I think part of this is it's an artifact of how this is drawn, but it will end up also being cis to the sulfur if you look at it carefully. Tim, does that make sense?
Yes, thanks.
Yeah. Okay, and so this brings us to the chemist of the day, who is, does anyone want to recognize either the chemistry or the photo?
Can I clarify something with the palladium problem?
Sure.
So the palladium bond would be broken during the oxidative addition and then reformed in the reductive elimination, right?
Oh, sorry. Thanks. Yeah, the way I had it drawn would be palladium 3, which is not accurate for a net 2 electron oxidative addition. Thanks. Was that Noor? Thanks, Noor, for clarifying. Anybody want to take a stab at the problem of the day, or the chemist of the day from last time?
Well, I will guess it's Franziska Schoenebeck.
Yes, thank you, Lynn. Franziska Schoenebeck. Very good. And just quick, in terms of quick bio, she's educated in Germany, Scotland, and the US. She did her undergraduate work at TU Berlin, and then PhD with an organic chemistry focus with John Murphy in Glasgow, and then postdoc with Ken Hauk, and then started independent career at ETH Zurich before moving on to her current position at RWTH Aachen. And among her many contributions, she's been involved in demonstrating the unique reactivity of dimeric palladium-1 species, as you can see here, through combination of experimental and computational studies, deep work in mechanistic organometallic chemistry as well. And she was recently in the new realignment of JAX appointed as a associate editor, despite being very early in her career. Okay, very good. Any questions on this problem?
I have one question. So like when you say the monomeric form didn't react, you are talking about the monomeric palladium 1 or monomeric palladium 0 or monomeric
that's a good question. I think what they did is look at monometallic palladium 0, because monometallic palladium 1s are, they're not as easy to come by. But I think it's debatable whether, like, what is the right monometallic palladium metal model complex to make this comparison. They report that they tried many and they gave 2 examples, but the ligands that they use in those 2 examples are not the same as tributylphosphine. So even there's some discrepancy. So yeah, thanks for the question, Lynn. Well, I'll leave this up in case people are still trying it down. So let's go ahead and move on to the next elementary step that we'll cover, which is 1,1 migratory insertion. So some quick features of this. as I said, there are two flavors of migratory insertion depending on the group that's being migrating into or the group that's migrating, depending on your perspective. There's 1,1, which is what you observe with carbon monoxide, with carbenes, for example. And then there's 1,2, which is what you'd observe with alkenes, alkynes, etc. The common features that both of these share is that there's no change in the oxidation state, that the two ligands, again, must be cissoid, and that upon migratory insertion, a new coordination site is opened up on the metal that normally needs to be trapped with an incoming ligand for the reaction to be thermodynamically favored. In cases where the migrating group has a defined stereocenter, like a secondary alkyl group, that stereochemistry is defined. That the statement I just made is generally true, that there are some exceptions when radical intermediates are involved, but in general, the stereochemistry is defined. And then, oh, I should delete this. This is one of the poll. Okay, hopefully nobody saw that. If you did, then you're going to get the poll question right. And you can, this process can be kinetically and also thermodynamically challenging in some cases, as we'll see, but it can be accelerated. And so ways to accelerate it are to have a more electron deficient metal center, to promote, to use bulky ligands, analogous to reductive elimination, where you're essentially squeezing out the two groups. When the carbonyl is more polarized, then 1,1 migratory insertion is favored. So often migratory insertion, not always, but often it's thought of as this alkyl group being nucleophilic and adding into the electrophilic carbonyl. It can happen with the opposite polarity, where the carbonyl actually is adding into the metal alkyl or metal aryl fragment, but in general, this is the preferred polarity mode, which means that a more delta plus carbon group on the carbonyl accelerates the reaction. And likewise, coordination of a Lewis acid would be expected to accelerate the reaction. And for reasons that are a little bit more complex, but do go hand in hand with this, the point I just made about a more electron poor metal, SET oxidation often is found empirically to accelerate 1,1 migratory insertion. Okay, Van, do you want to initiate the poll for anyone who didn't see it? And if you did see it, just please humor me and pretend that you didn't. Oh, can you go to the second one first? Or not? Yeah, okay. Okay, so the question reads, for an isostructural series of metal alkyl species, what would you expect to undergo faster 1,1 migratory insertion with a carbonyl ligand, 3D, 4D, or 5D? And then I'll call on someone to give their explanation. So think about that for 15 seconds. Okay, can you start the poll closing or whatever, man? Give your last thoughts. I think looks like everybody's there. Okay, and the winner of the vote was 3D. Some people also picked 5D. Nobody picked the Goldilocks 4D. So let's hear from Alex. What did you pick and why? Oh, Alex, I don't know if Alex maybe stepped away from the computer. What about Jun Chen? Are you there? What did you pick and why?
Yeah, I'm here. I picked 3D.
Okay. And why is that?
Yeah, I rationalize that maybe the rate is showing how this metal can stabilize the vacancy empty orbital. So
Okay.
if it's a so if it's a 3D, for early metals, they their 3D orbitals that are energy 3D orbital energy are low, I guess. So yeah.
Yeah, I think you're getting at the right point here. Anybody want to expand on that?
Is 3D the smallest d orbital?
It is, yes.
So I guess it is the smallest orbital. So the two ligands will be the closest and react faster. So it's a kinetic question.
Okay, yeah, I think that's one reasonable explanation. There's also a significant, it turns out, thermodynamic, even though the question is about kinetics, there's a significant thermodynamic component to the answer, namely that, as we saw, 3D metals form much weaker bonds with organic fragments than do 4 or 5D metals. And this leads to ground state destabilization. So you can imagine the starting point, if the transition state barrier is similar in this isostructural series, and then you have successive ground state destabilization, that will lead to a rate acceleration. Okay, very good. Any questions on that? So this leads to this a springboard into this question of migratory aptitude, which is really a question of, given a pair of organic ligands, which is going to be more likely to migrate into the metal carbonyl bond. And the overall upshot is that this is somewhat complex, and that the reactivity trends reflect both kinetic and thermodynamic factors. And part of the reason that both are reflected, even when we're just focusing on let's say, even in the question you just saw where you're just focusing on rates, there's a significant thermodynamic component, is precisely that you have this ground state stabilization or destabilization. And so in considering migratory aptitude, I think there are two questions that should be going through your mind. The first is just, is the process thermodynamically allowed or thermodynamically favored or not? And the answer is typically not for the ligands highlighted in this gray box. Hydrides, alkoxides, metal amides, silyl groups. These are less common. Empirically, it's found that these undergo migratory insertion into a carbonyl less commonly. There are some notable exceptions, particularly with early metals and high-grade migratory insertion. But in general, this is not thermodynamically favorable and thus does not take place. So that's the first question to consider. And then the next question is, if you're looking within a series where you know that all of the ligands do have thermodynamically allowed migratory insertion, then how do you sort through the kinetic trends? And so a summary of migratory aptitudes within a series that all undergo migratory insertion is shown here. So the general trends are that tertiary alkyl groups migrate faster, then do secondary, then do primary, then does a simple methyl group. And then all sp3 hybridized migrating groups migrate faster, then do sp2 hybridized, then do sp hybridized, and particularly sp2 hybridized that are electron poor in nature. So this is a little bit counterintuitive, I think, because it's sort of different than the trend that we see in reductive elimination, where high S character normally makes reductive elimination more facile. And here too, within this series, even though we're just talking about kinetics, there's a big thermodynamic component, because when a complex undergoes migratory insertion of a big tertiary alkyl group, it's a much stronger thermodynamic driving force than in the case of a methyl. So you get this significant ground state destabilization that leads to kinetic rate enhancement. And this is a similar argument to what you saw before in the 3D, 4D, 5D series. Okay, any questions on that? Okay, so now let's just look at some general, I mean, we won't take a deep dive into the sort of the rate laws of all the different possibilities and as a function of different metal, different ligand, and all those things. But I do want to give you a general appreciation for sort of distinguishing features and different scenarios that you can, different regimes that you can be in migratory insertion. So let's consider the migratory insertion kinetics of this methyl manganese pentacarbonyl complex, which was just abbreviated S in the rate equation below. So this is going to undergo 1,1 migratory insertion from the methyl to the carbonyl. That will open a free coordination site, and that needs to be then trapped with ligand L. So the first step is shown here as reversible. The forward rate constant is abbreviated K1. The reverse rate constant is shown as K-1, and then the trapping step is shown as K2. So we can just quickly put together a simple rate expression for formation of product, which is equivalent to consumption of starting material. We would then make a steady state approximation. The step that we're first we define the rate as the rate of the rate of product formation as the rate in which the intermediate reacts with the ligand, use the steady state approximation, and then we can plug and chug and do algebra that I know you're all capable of doing to arrive at a statement, an expression for what the equilibrium concentration, or sorry, what the intermediate concentration is as a function of the other variables. we can then plug that into, so the steady state approximation allows us to determine a equation for the intermediate concentration, and we plug that in to this step, the rate expression for this step. And then what we get out is an expression that looks like this. And if you don't want to write this down yourself, you can just take a screenshot. But what I do want to take a minute to work through together are the different possible scenarios that can then arise. And I'll first state them in terms of the math, and then I'll state them in terms of the intuitive chemistry. So let's consider a situation where K1 and K2 are much faster than K-1. In that case, this rate expression simplifies to a first order regime just in the substrate. And we can call this scenario Al always traps. So let's zoom out on that. So what that means is that the reverse step is very slow in this scenario. So in every atomic event where the methyl group migrates, it is successfully trapped by the ligand. And that's this scenario and what the rate expression looks like. You can also have what's, in a sense, kind of the opposite scenario. And you can think of this as like, rather than getting trapped 100% of the time that the methyl group migrates, it gets trapped a fraction of the time, 1/1000th of the time or something like that. And in this case, now you have a different overall rate law. You have overall second order kinetics. Where it's first order in substrate and first order in ligand. And we'll call this almost always goes back. And then this third scenario is somewhere in the middle. And this one is just intermediate order where nothing cancels. We can also call this second scenario, if it helps you think of it this way, is the rate governed in second step. So part of the reason why I think it's useful to do an exercise like this is that this is a pretty, I mean, in some ways, as organometallic reactions go, this is about as easy as it gets. You have one group migrate and then you trap, and you see already the mechanistic complexity and in terms of how this manifests in the underlying rate laws. So a couple of takeaways here is, one, you can distinguish between these possibilities using carefully designed kinetic experiments. Two is that even in individual elementary steps, there can be this level of complexity. And then when you think about catalytic processes, you not only need to zero in on what step is turnover limiting or rate limiting, but within that step, there are these different potential scenarios. So that creates quite a bit of complexity, which makes it both fun and challenging. Okay, let's jump over to problem of the day number 1 from our day 6 worksheet. Is everyone able to see the screen share? Okay, thank you. So this one will be a springboard into the discussion topic that we'll cover next. So question 1 asks you to take a look at this. It's actually quite similar to what the complex we just went through the rate analysis, the kinetic analysis of. It's a pentacarbonyl manganese, but in this case, instead of the methyl, there's an acyl group. And then something is going to happen. There's some undefined intermediate that I'm asking you to propose this structure of, and then it will get you to, and then something else is going to happen. So I'm not being very helpful here in explaining the question. And then you'll get to either complex A or complex B. And so take 30 seconds to think about that. And Van is going to queue up a poll. Or can we go back to the, okay, great. And so this asks you just about the product, whether product A or B is formed. And then I'll call on someone and ask for the intermediate structure. Okay, I think almost everybody's registered your answer, so please do so if you haven't. If you need to guess, you can guess and we'll discuss it all together. Okay, you can end the poll then. All right, the overwhelming majority of people picked A, though that alone doesn't mean that it's right. So Tiffany, can you walk us through your thinking here, if you what the intermediate was, and then how that would lead to either A or B? And I'm going to switch over here before I forget to my iPad. I always forget to do this. Okay. Okay, Tiffany, what do you think?
Yeah, so I picked A for this one. I guess somehow in this reaction, you need the methyl group to insert and then one of the carbonyls to leave. So I guess there might be I'm not really sure what the intermediate would look like, honestly.
Okay. I think you might be maybe are overthinking it. So this step is it's a little bit of a twist on what we just saw. It's basically what we just saw in reverse, which will lead us to our next section, which is alpha elimination. And so one of the requirements you saw in the 1-1 migratory insertion, or one of the features you saw, is that after migratory insertion, it opens up a coordination site. So it would stand to reason that when you're going in the reverse direction, you need a coordination site open in order for alpha elimination or retro 1-1 migratory insertion to take place.
Okay, so then
Does that make sense?
would one of the carbonyls leave and have the coordination site and then the methyl move in?
Perfect. Okay. Nailed it. Okay, and then now you said the methyl is going to move in. We normally draw that the migratory insertion as yeah, let's draw it with arrows like this. Okay, and then that would get you exactly to A. Maybe I'll ask one follow-up question, Tiffany. What would happen if in this first step, rather than the carbonyl that I depicted leaving, what if like say this carbonyl left?
I guess it wouldn't be very productive.
Right, exactly. This probably may very well happen, but it is non-productive. And this is another key point, is that, you know, sometimes you might be asking yourself, well, how do I know this leaves or the other leaves? I mean, you can always just walk down that road. Like, let's say the carbonyl that's trans to the acyl leaves. What happens? Can anything happen? Not really. So then what would actually happen is the carbonyl just coordinate again, and then you have a chance for another ligand to leave. Okay, super. Anybody have any questions on that?
It may not be productive, but how would you be able to tell if like the acyl dissociates at all? Like, do you think it does?
To give an acyl anion in that case, Daniel?
Yeah.
I think if I had to hazard a guess, I would say it probably doesn't. I mean, it could. It's interesting. I guess it could potentially homolyze and recombine. That might not be such a. I would expect like formation of a discrete acyl anion to be pretty high energy and not favorable. But it's not impossible that you could get homolysis of that metal acyl bond. And yeah, then I guess there are experiments you could think about trying, like radical traps, to see if you could capture that and get evidence for it. Great, thanks, Dan. Any other questions? Okay, so this is as I said, a prelude to alpha elimination, which we're going to cover quickly. Because again, this is the microscopic reverse of 1-1 migratory insertion. So the same trends that you just saw basically are going to hold in reverse. So I'm going to cover this section by going through two case studies that you might that will potentially be relevant to you. So one type of reaction we'll cover is the one that we just did in this problem set, which is decarbonylation. And hopefully from that problem, you get a sense at mechanistically how this is working. And so we can now take this a step further and actually think about a productive reaction, or a reaction that's potentially productive in synthesis. So we'll start out with this complex shown here on the left. Does anyone know the name of this complex?
Is this one Wilkinson's?
Tim's proposed. Are you going to keep guessing Wilkinson until you get it, Tim?
Yeah. Yes.
So this is Wilkinson's catalyst. Okay, now since I've got you unmuted, Tim, or maybe you already muted yourself, walk me through this. So I'm asking you to think about what's happening in this step. First, you lose a triphenylphosphine, and now you have a aldehyde present. What do you think might happen?
Okay. So I think that you will get an oxidative addition into the carbon methyl bond.
Okay, I like what you're thinking, oxidative addition. Now you have two possibilities here.
What's
You have
the migrating group? I forgot. Oh, does it? Oh, the hydride, the H, and then the acyl.
okay. And if you had to give, without the sheet, if you had to give an explanation of like why it would be the CH and not the C methyl, what would you say? Any thoughts, Tim?
Yeah, I'm thinking. I guess because the H is smaller and can migrate quicker.
Okay, I think that's a reasonable explanation. Certainly, the bond that you're breaking is much more sterically accessible. The sigma star antibonding orbital is much more accessible than in the case of the methyl. Okay, and then now let's take this one step further. Based on what you've seen so far, what might this go on to continue to do?
Are we going to do another oxidative addition or I guess 1,1 insertion into the methyl carbonyl bond?
All right, got it.
And then you lose methane or something?
You lose methane or something?
Well, I'm not too sure. I think you would maybe lose the chloride and get another open site for something else to happen.
Well, why was your initial thought to lose methane?
Because I guess it's more labile than carbon monoxide. And there's cis.
Yeah, you're gonna feel like I'm trying to trick you. I think you got it.
Okay.
I was just asking you to sort of to think through why. So among factors you could consider, this reaction, loss of methane, will have a strong thermodynamic driving force because you're creating a gas. In this specific case, although that's not actually necessary for this reaction to take place.
So would you say that the thermodynamic driving force of generating methane gas compared to having the pre-existing carbon monoxide, I guess, dissociate is just greater?
Well, loss. So what was your other thought? Was that you would lose CO? Is that right?
Yeah, I mean, I guess just playing a little bit of the devil's advocate there with losing the CO, because I guess they're both gases, but I know that the CO doesn't leave here.
Yeah, part of what's going on here is, remember, CO in general is going to form strong bonds to metals, particularly low oxidation state metals. And that bonding interaction is going to be stronger than the other bonding interactions between methyl or the hydride.
For the catalyst to turn over, the carbon monoxide will be lost, right?
That's right. This reaction generally does not turn over catalytically, although it is a name reaction. Does anybody recognize the reaction? If you said Wilkinson, you'd be half right. This is the Suji Wilkinson decarbonylation. But yeah, I think that I couldn't see who unmuted themselves for that, but you've pinpointed the exact challenge of turning this over and what you'd have to think about to render it catalytic. And there are catalytic process. The original reports that were stoichiometric. There are ways to carry this out catalytically, but you've zeroed in on exactly what you have to consider. Good. Any questions on that?
Yeah, I have a quick. Oh, sorry. Go ahead, Nora.
Sure.
No, go ahead.
Okay. So the switch from octahedral back to square planar, does that happen automatically upon elimination? Like essentially, do you have your chloride moving in space?
You will eventually get to square planar.
Okay, but for like after elimination, is it in almost like an octahedral with two empty spaces, or does it like, is that not really the way to think about it?
I think you can think about. This is maybe like I don't know if it's helpful, but if you like kind of mentally simulate what will happen as these two bonds. I don't know. Can you see my pointer or not?
Yep.
Okay. As the hydride and the methyl come closer together, then all of the other ligands, you can think if you're from their perspective, where you would want to sit on the octahedron to be lowest in energy, and it's not, the lowest energy form is not for them to just remain statically exactly where they are, and so they're already starting to sort of flex into position to avoid these major geometric rearrangements that were sort of what you were thinking of, where you'd like what I think what you had sort of pointed at was that after reductive elimination, you would have what would the shape be? Like a T plus.
Kind of.
Yeah, kind of like a square pyramid sort of thing. But I think in practice, that geometric reorganization is happening in a concerted way as with reclamation. Yeah, great question.
I have one more question about this complex. Sure. So for so the final product complex, I guess, would it sort of be able to dissociate the other two phosphates sequentially and sort of turn over twice more, or electronically is it not favored to undergo oxidative addition because of the carbonyl?
That's a good question. I don't know, Tanner or Van, you can chime in here if you know off the top. I think after one, it has become deactivated for the oxidative addition.
Okay, thanks.
Yeah, nor this complex, the final product is actually also a commercial catalyst you can buy, and in this case, you can't really get a phosphine to dissociate below 100 degrees. And sort of also to partially answer Kelly's question, I gave this same explanation, I believe, to Tawe when he asked which group will be the one that migrates into the square plane. As you would see, Kiri said, you have like this T-shaped intermediate, and one explanation you can usually rationalize this with is for this D6 complex, you can draw the MO diagrams and see which orbitals the electrons will be in, and then which orbitals would stabilize key interactions, such as the pi back bonding to the CO ligand. And you would sort of want to maximize that interaction to make this transition state most stable and migrate the ligand that would be minimally affected by that. So in this case, it would likely be the chloride if you have your the electrons in the XY, YZ, and YX orbitals. Does that sort of clarify things a little bit for this specific one?
Super. Okay, let's keep moving forward here. So another type of alpha elimination that merits discussion are, oh, I have this as carbene insertion, but it should be carbene insertion is more like the 1-1. It should just be like carbene as ligand. Carbene. Okay, so let's consider the example shown, this tetraalkyl tantalum dichloride. So the first step, I think, should be hopefully look a little bit familiar based on what we've already done in class. So what would you expect to happen here? Brendan?
I guess you just swap out the chloride just through like a transmetallation or.
Beautiful, okay. And what's the driving force of this reaction?
Salting out.
Perfect, okay, oops. So AFPON treatment with neopentallithium, you get this double transmetallation, and then do you want to hazard a guess to take this one step further? Brendan?
So I guess we're going to try and generate a carbene somehow. Let me think here. Just sort of, this doesn't look like a carbene per generator from what I'm used to seeing, so it's a little hard for me to see. I guess in this case you might.
I'll draw this in a suggestive way.
Oh, okay. So I guess just sort of following the sort of template you have above there, you can sort of migrate the hydride onto the tantalum, and then form the carbene there. Yeah.
Okay, and does this look happy to you?
No.
Okay, so what do you think might happen next? Sorry, I keep picking on you.
Let me think here. Okay, so we did the transmetallation, we formed the carbene. All right.
So think about what we saw last time.
Oh, just a quench of the alkyl species, and then
so in this case you can lose neopentane. Oops, got carried away there. And this, by all accounts, but I've never made it myself, is a beautiful orange solid. So congratulations, Brendan. You've just finished the first ever synthesis of a Schrock carbene, and you'd be well set for a Nobel Prize if it was the 1970s. So
Too
this
bad
is
it's already known.
This is the route that was taken to the first alkylidine, Schrock type alkylidine, and then by Schrock himself, I think when he was working in industry, if I'm not mistaken. And this carbene, as we'll talk about carbene in the next lecture, this carbene had properties that were unlike any other carbene known, which is why it got its own name, and ultimately led to Schrock's interest in olefin metathesis.
Kiri,
yeah.
What's the geometry of that product? Is it square planar?
It's
I would think
not
so.
Square planar.
Is it like a Wittig reagent?
It's like a pyramid, yeah, like a Wittig reagent, I guess, is a one, or sorry, like a phosphine oxide, where the 3 alkyl groups are pointed down. And
yeah, I think it's pseudo tetrahedral, but I can double check this. It's a good question.
Why are alkylidine complexes more common with first row? Or sorry,
Yes, that's a great question, Camille. And if you're not satisfied with the explanation I give next class, then please re-ask this question. Okay, so now I have a reminder to myself to cover problem of the day number 2. So let's take a look at that. So we're going to stay within the theme of tantalum chemistry. So in solution in deuterobenzene, you have this diphosphino, dichloro, tantalum, alkyl, olefin complex. It's a bit of a mouthful. And this is in equilibrium with another form that is isomeric. So what is the predicted structure of A, and mechanistically, how would you form it? So I will give you a minute to think about that while I draw this. And then I will switch over to switch back to my iPad. Okay, Jung, are you there? I'm not hearing him. What about Yukun? Yukun, are you there?
Sorry?
Yes. What do you think the answer is?
Let me think. So I think maybe it will use a hydrogen chloride.
Okay, that is reasonable, but I told you already that it's going to be isomeric.
Okay.
So as a hint, what happened in the previous problem when we had this tantalum alkyl?
I think.
I'll draw it here in a suggestive way for you. Okay, what do you think, Yukun? I've got the suggestive drawing here for you.
I think it will form a cabin here,
Okay.
and yeah, I'm wondering where the hydrogen will go.
Aha, well, we already have a sneak preview if you looked at the
Oh
bottom
yeah, I
of
see,
the screen.
yeah.
Ah,
So the hydrogen will migrate to the olefin, the
beautiful, okay.
ethylene, yeah.
Almost like we planned it that way. Okay, so we see, as Yukun told us, alpha hydride elimination to give the tantalum carbene hydride complex, hydride migratory insertion into the associated alkene, and that gives an alkyl tantalum carbene. And because these are in equilibrium, you can assume that they have similar stabilities. Okay, super.
Kiri,
Yeah.
Kiri, I have a question. I was wondering how can I push electrons in the hydride shift? Like where, like is it like a 2-electron process from the hydride to the tantalum?
Yeah, this is a little bit tricky because as we'll see when we learn about carbenes next class and how to count electrons, you can actually think of this as a formal like oxidative addition. So if you wanted to push electrons, you would push them like this, where you're pushing electrons off of the metal because the tantalum carbene hydride will be a higher oxidation state formally, because the Schrock type carbene counts as a X2 ligand.
So
Van
would
is
this
looking
apply,
disapproving. Is that not right, Van?
would this apply in like the other example that you gave before? Because it was a D0 tantalum, no? Prior to the shift.
Yeah, I think this first mechanism, the all neopentyl, is kind of like argued about. Like some people say it's just the concerted hydroabstraction by one of the neopentyl groups, but the second one is,
Yeah, this one you can, okay, what Van is saying in terms of pushing electrons is this one you can draw like this way. Also, that's an alternative.
I have another question.
Yeah. So I guess and then you draw like this, I guess, Omar, if you want to think of it that way. These are, I mean, this is, I think, from my perspective, where the oxidation state formalism breaks down a little bit. I mean, do you really think that metal is undergoing like a 2-electron oxidative addition just to tautomerize? I mean, that's probably not a good physical reflection of what's going on at the metal center. But that's what we would say formally. Sorry, there was another question.
I'm wondering that if the chlorine atom could undergo a 1,2 migratory insertion onto the ethylene ligand.
Chloride is not typically good at 1,1 or 1,2 migratory insertions. It's sort of at the same bin as alkoxides. So it is not reactive. And
well, I have the same question, but like applying to the alkyl group. I mean, can you do migratory insertion to the alkaline and then just do the alpha hydrogen elimination?
Yeah, we'll talk about this. In general, if you have the choice between for a 1,2 migratory insertion, the trend is a little bit different than what we saw with 1,1. So in a 1,2 migratory insertion, if you have that choice to migrate a hydride or an alkyl, you should always the hydride will migrate preferentially. And I'll talk about why that is briefly. So follow up if it's not clear from my explanation, Wayne. Okay, so I think there are some great questions here that really get at the heart of this question of 1,2 migratory insertion, which I think we'll talk about in the context of alkyl addition, or we'll talk about in the context of addition to coordinated olefins, but the logic is the same, whether it's an olefin or an alkyne, or even things like carbonyl containing compounds like ketones. The logic is the same. And so you'll also hear this, just as a point of nomenclature, you'll also hear terminology like metal hydride groups or metal alkyl groups undergoing hydrometallation or carbometallation. And this is really, you can think of as just synonymous as with 1,2 migratory insertion. As I said, metal hydrides are fastest reacting within this class. And so let's kind of walk through this here left to right on this figure. So if you think about a metal hydride approaching an olefin, well, the olefin will first coordinate, and then you'll have this concerted transfer. After you form the metal carbon bond and the new CH bond, then there's another intermediate here that can be generated and is important in the reverse reaction. Does anybody? This is called the agostic intermediate. So if we go left to right, we get 1,2 migratory insertion. We make this agostic intermediate, and then we get CC bond rotation and occupation of the open coordination site with the ancillary ligand. And this process is reversible and often can happen fast and multiple times. So now if we think about a given alkyl metal intermediate, then provided that alkyl metal intermediate has hydrogen atoms at the beta position, a hydrogen atom can rotate up to the appropriate position, form an agostic interaction, and then that can trigger the reverse process, which is beta hydride, in this case, elimination. And so the nomenclature here in terms of the Greek letters, beta is referring to the position with respect to the metal. well, I should, just in case anybody's curious, there's one molecule, there might be more than just one, but one prominent example of a molecule that can undergo both 1,1 and 1,2 migratory insertion. I don't know if anybody has encountered this. I guess Omar would be the person, or Camille. So SO2 is the answer here. So you can add doubly across sulfur or across sulfur and oxygen. That's just a piece of trivia, but in case people are interested. Okay, so this was this reactivity summary table is I think really getting at the heart of some of the discussion coming out of the last question. So looking down the first column, this is what we covered in 1,1 migratory insertion, where we said that alkyls are the fastest reacting and followed by aryls. And then hydrides are typically unreactive. And that's because of a thermodynamic argument. Remember here that metal hydride species, a metal hydrogen bond is stronger than a metal carbon bond. And so when we talk about ground state lowering or raising, that's what we're referring to here. So metal hydrides typically won't react with CO, and then the trend is as a first approximation sort of reversed when you're talking about alkene insertion. So the fastest reacting are typically metal aryls, then metal alkyls are, the fastest reacting are metal hydrides, then metal aryls, and then metal alkyls can react, but others things will react first. I guess maybe I should sort this. If I sorted this in the order of reactivity, maybe that would be better to do. I'm using all of my notability skills here to try to do this. Okay. And so with metal hydride, in terms of insertion to CO, we said that was the big consideration there was thermodynamic. And then in comparing for the alkene series, typically the dominating factor here in terms of relative reactivities is thinking actually about the transition state structures and the energy differences at the transition state and the underlying kinetics. So groups that are small, groups that have high S character, migrate into alkenes faster because the corresponding transition states are less encumbered. Okay, so quick regioselectivity tutorial on metal hydride insertions. I think this will probably be familiar with a lot of people, familiar to a lot of people. So depending, if you consider a terminal alkene, how the metal hydride inserts will depend on what the identity of the R group is. So with a aryl substituent, typically the hydride is transferred to the terminal position and the metal is transferred to the benzoic position, or in case of a 1,3-diene, the allylic position. This is, I think there are two considerations here. One is the ability to form a pi benzyl or pi al intermediate that can be haptotropically stabilized. So the ability to toggle between 801 and 803 is a stabilizing effect. The other thing that sometimes goes unnoticed, but I do want to take care to emphasize, is that when you're talking about regioselectivity and the kinetics and thermodynamics of this process, you also need to think about the other end of it, not just the metal carbon bond you're making, but the CH bond that you're making. And as you can appreciate, forming this CH bond at the benzylic position versus the non-benzylic position the non-benzylic position is a much more stable CH bond. So you have two factors that are both arguing in the same direction. With an electron withdrawn group here, so things like acrylates, you get preferential hydride insertion into the beta position, and this probably looks familiar from reactions like conjugate reductions, or conjugate reductions followed by enolate trappings. And then with simple alkyl groups, you have a tendency to put the metal at the terminal position, because metals, by virtue of being big, prefer to be at less hindered carbogenic sites. So in this case, sterics will dictate that the thermodynamic preference is for the metal to be at the terminal position. I did want to take just 1 minute to provide a little bit of additional commentary on this term agostic interaction before moving forward. And so this was a term that was coined by Maurice Brookhart and Malcolm Green, I think during Brookhart's sabbatical stay at Oxford, where Malcolm Green worked for most of his career. This has to do with the observation that's summarized here. Again, you shouldn't feel the need to write this down. If anything, you can take a screenshot, or you can look at these references where they have these same diagrams. But this came from the observation that in the crystal structures of complexes like this alkyl titanium, the bond angles and bond distances suggested that there was an interaction between a CH bond and the metal center that was not consistent with things that had been documented before in the literature. And so they term this agostic interaction, coming from the Greek term. So remember, this was happening at Oxford. So they're having dinner with classicists, and the classicists are proposing these fancy names. So that's where this term agostic comes from. It's from the Greek, to hold close to oneself. So the metal is holding the CH bond close. And this is a term that's specific to alkyl metals and the intramolecular interaction between the CH bond that takes place here. And I've learned, if you are writing an email and you type agostic, you use Gmail, for example, it will get auto-corrected to agnostic. So you have to be on guard. Although I've been dealing with this all my life, because my name always gets auto-corrected to God knows what. I think John Kerry during the presidential election for many years. Here I'm dating myself, but and so one of the kind of interesting features, I'll just take 30 seconds to unpack this. If you do the electron inventory on this complex, you'll see that it's titanium 4+, D0, and then overall electron count of 12. But actually, if you count the agostic interaction as a ligand, it can change the overall electron count. So, like as a first pass, don't overthink this. If you have no reason to think there's an agostic interaction, don't draw one in. But if you have strong structural evidence, then actually there's the ability of the metal to sort of stabilize itself when the metal core doesn't have enough electrons to be happy.
So then, Kiri, in that crystal structure, was that chloride ligand on there as well?
Yeah, it's the structure. It's the structure drawn.
Okay. Was it like a distorted octahedral? Or bipyramidal.
That's right. Yeah. So the overall geometry is a distorted octahedron. Yeah. Thanks, Daniel. Okay. So I see we are out of time. So we will wrap things up here, and then I'll take a few minutes at the beginning of the next class to wrap up the last couple sections, namely a quick primer into beta hydride elimination, which would just be the reverse of what you saw here, and then transmetallation. We'll talk about carbene ligands and answer some of the questions that have come up during today's class. And then we will be fully primed to dive headlong into catalytic reactions by putting all of this together. So thanks, everybody. And you're dismissed until next time.